Hi all. In the last class, we have discussed what is the difference between a pure state and a mixed state and how to use the density operator to represent a mixed state. So today, we are going to introduce the density operator approach in Jaynes Cummings model. Okay, so we have already discussed to solve the equation of motion of JCM if both atom and field are in a pure state. It is state which are represented by the kate vector. Okay, so next we can discuss the solving JCM with an atom or field or both in the mixed state. So in case of mixed state, we have to use density operator to represent the state of such system. Okay, so we can start with a pure state. Suppose an atom which is having the pure state, so either it can have the ket E or ket G, or it can be in a superposed state of ket E and ket G. There can be different kinds of superpositions. Okay, this superposition, the first superposition is of equal probability. It can be either in E or G with equal probability. But if you look at here, this particular superposition, this ket E is having the lower probability. It has a probability of 1 by 4, and the ground state is having probability of 3 by 4. But anyhow, the sum of both the probabilities must be 1. So in general, the pure state of atom I can represent as C1 ket E plus C2 ket G, and it is usually called the coherent superposition of states. Now, for mixed state of atom, the density the state is represented in terms of density operator and density operator. So here we have two possible state, the excited state and the ground state. So the density operator can be represented as the probability of the excited state, then outer product EE, then the corresponding probability of ground state, and an outer product of GG. So this will be represented as the density operator or the state of the system in a mixed state. So here PE, PG represent the probability to find the atom in excited and the ground state respectively. The state represented by the rho is usually called the incoherent superposition of states. So in the same way, we can represent the mixed state of the field using the density operator. So it can be represented density operator of field. It is sum over n, Pn, the outer product Nn. Okay. So remember, ket n is a pure state which is having n number of photons, or it is called the Fock state. Okay, so in general, the field can have many number of photons. So its incoherent superposition is the outer product of each state, then multiplied by the corresponding probability. Okay, now let's consider a JCM model, the Jaynes Cummings model, with a Hamiltonian interacting picture under resonance. So the interaction part of the Hamiltonian is given as, so this we already represented the HI, the interaction part of the Hamiltonian. It is h cross lambda a sigma plus then a dagger sigma minus. So this can be our equation number 3. Okay, so this is we are considering for simplicity. Okay, and we have already seen the last lecture the equation of motion for a density operator. So here density operator, suppose rho is the atom field density operator at time t. Then the time evolution is given by IH cross d rho by dot t is equal to the commutator HI rho. So HI is given from equation number 3. Okay. Now the time evolution. So in interaction picture, the time evolution of any operator. So rho of t, it is simply ui of t, rho of 0, ui dagger of t. So this ui of t is the time evolution operator in interaction picture, and so this can be equation number 5. And ui of t is given as e raised to minus I hit by h cross, and hi is already known from equation number 3. So this can be written as e raised to minus I lambda times sigma plus a plus sigma minus a dagger times t. Now we are going to use the standard result. Okay, so now our aim is to find the matrix form of ui. Okay, so in order to find the matrix form of ui, so first of all I have to know one identity. So the identity e raised to minus I lambda t times sigma plus a plus sigma minus a dagger is cos of lambda t, the square root of a dagger, minus I sigma plus a sigma minus a dagger. So all these are operators. And then then divided by square root of a dagger sine of lambda t is the square root of a dagger. So let this can be my equation number 7. Okay, now I already said we are going to find out the matrix element of ui. So in the basis state of atom E and G, I can find the different matrix elements of ui. The first matrix element will be e ui, the inner product e ui e. And if you calculate e ui e using equation number 7, so how to write it? So using 7, so using 7 e ui e would be e cos of lambda t square root of a dagger minus I sigma plus a minus sigma minus a dagger divided by square root of a dagger, the sine of something times e. Okay, so this inner product can be split into two. The first part of the inner product minus the second part of the inner product, but the second part of the inner product will directly go to 0 because we have a sigma plus here and sigma minus. So sigma plus acting on E directly becomes 0 and sigma minus acting on E will become G, and the inner product EG is 0. So therefore this part is going to cancel and we have only E cos of lambda t square root of a dagger E. So cos of lambda t square root of e dagger can be taken outside from that inner product, and we'll get just simply the inner product between e and e, that would be 1. So finally we'll get this particular the first element of the ui matrix is simply cos of lambda t square root of a dagger, and I am going to represent that by the symbol c of t. So these are the symbol which is already used in your textbook, so I am not going to change all these notations. Okay, so let us remove these steps. Okay, so in the same way you can find out all other matrix elements. The first matrix element is found to be cos of lambda t square root of a dagger represented by c of t, and let this be my equation number 8. So the second matrix element would be euig, and that is minus I times a square root of a dagger sine of lambda t square root of a dagger. So let this be equation number 9. And similarly we can find the third element GUIE, and that is simply s dash of t, because this is your s of t and this can be represented as s dash of t. And finally the last element GUIE G is cos lambda t square root of a dagger, and that is represented as c of t. I think there is a small correction here. This must be plus. Okay, so let this be equation number 10 and this be equation number 11. So we can clarify this equation number 10. So equation number 10 is G U I E, and this will be have two parts. One is G, the UI is cos of lambda t square root of a dagger times E minus G I sigma plus a minus sigma minus a dagger divided by square root of a dagger times E. So sigma plus E will directly become 0 and sigma minus E will become G. So sigma plus A effect will not be there, and sigma minus acting on E will become G, and Gj in the inner product Gg would be 1. So therefore, so this becomes the first term is will directly go to 0. Here this effect will be 0. So this become minus G minus a dagger divided by square root of a dagger times E. So this minus and minus will become plus G. So this will be G. So this become minus and minus become plus, would be a dagger divided by square root of a dagger. And I have forgot to write this sign part, so there will be sine of lambda t square root of a dagger here. So that would be here sine. sine lambda t square root of a diagonal. So therefore this would be okay, so there is an I common here, I. So this will be plus I a dagger divided by square root of a dagger sine of lambda t square root of a dagger. So let that is be equation number 10. Okay, so then ui of t is a matrix in two-dimensional subspace, and ui of t I can write as there are four elements: c of t, s of t, and s dash of t, c of t. Okay, because these are the simply the matrix element ui. The first element is e uie, then e uig, g uie, and finally we have g uig. So this is the the convention we have followed. And if you take its dagger, so if you take the dagger, this becomes c of t minus s dash of t minus s of t and c of t. Okay, now the density operator of the combined system, that is the atom field system, we can always represent as a tensor product between the density operator of the field and the density operator of the atom. Okay, so let this be my equation number 12. This will be equation number 13, and this can be equation number 14. Now suppose the atom is initially in the excited state, then the density operator for the atom, operator for the atom is simply 1 EE and plus 0 GG, because the atom is already in the excited state, so there is no probability for the ground state. Okay, so this matrix we can obtain, so this is at time 0, so rho a of 0 is simply using the same convention, it is E rho a0 E, then E rho a0 G, G rho a0 G, and finally we have G rho a0 G. So this is the convention, and using this convention we have obtained this matrix, so that this be my equation number 15. Now therefore the density operator at time t equal to 0 in general can be rho of 0 is rho f of 0, the density operator of the field, times the matrix product of rho a of 0, and rho a of 0 is already obtained from equation number 15, it is 1000. So this can be written as rho f of 0 0 0 0, and this be my equation number 16. Now this is the total density operator of the combined system at time 0. So at a later time we can find out using the time evolution equation. So using the time evolution of interaction picture, the rho of t is nothing but ui of t, rho of 0, and ui dagger of t, and we have already found what is the expression for ui of t and ui dagger of t earlier. Using equation number 12 and 13, I know what is my ui and ui dagger. So using 12 and 13, I can substitute my ui of t and ui dagger of t and do this matrix multiplications, and we'll find that that will be equal to the density operator at a later time of the combined system, the atom field system, would be c of t rho f of 0 c of t minus c of t rho f of 0 s dash of t, then s dash of t rho f of 0 c of t, and finally minus s dash of t rho f of 0 s dash of t. So our next aim is to find the reduced density matrix or a reduced density operator. So the reduced density operator of the field can be found by tracing over the atomic states, that is the rho f of t, the reduced matrix of the field. It is at time t, it is uh, simply the tracing out the atomic states. So we have to find the inner product of the rho of t in the state E and the state G and just sum it. So that is what is done by the tracing over the atomic states. Okay, so you can do this calculation because we already know we have already found the expression for rho of t, and just take the inner product. So the E rho of t E would give the first element. So this would be E rho of t E, and this would be G rho of t G, and just take it sum. Okay, so there is a minus sign in between, so therefore we will get a minus sign. Now the matrix element of any density operator of the field is given by rho f of ij of t is I rho f of tj. So similarly, density operator for the atom can be found by tracing over the field states. So that is rho a of t, because the field can have many possible states. In case of atom, there is only two possible states. That is why we have taken only the inner product with E and inner product with G. But in case of the opposite, in case of atom, we have to trace it over all the possible states of the field. So it would be the sum over n is equal to 0 to infinity, the inner product n rho of t n. Okay, so the matrix element of rho of t are, so the first element rho a of t, it is e sum over n equal to 0 to infinity n rho of t n e. Okay, so what is meant by this? Because we know the reduced density operator A. So its first matrix element would be E rho A of T E. Okay, and rho A of T is already known from this equation. Okay, let us give some equation numbers. So we have found equation number 16. This rho of T, my equation number 17. So this would be equation number 18, can be 19, 20. Okay, so let this be 21. So from equation number 20, I can substitute my rho of t. So this will be E sum over n equal to 0 to infinity n rho of t n times E. So that is what is written in equation number 21. And similarly, we can find out the other matrix elements, the gth element and ejth element. So this is the first element, and the second and third element is here, and this is the last element. So these are the matrix elements. So that this be equation number 22 and this will be equation number 23. Okay, so if you look at the first element of reduced density operator for the atom, and the last element of reduced density operator of atom, so they are the probability to find the atom in the excited and ground state respectively. So recall your incoherent superpositions. So if you have incoherent superpositions, so rho A we written as PE outer product EE plus PG outer product GG. So here the first element, the rho A EE is nothing but PE, and rho A GG is nothing but your PG. Okay. So this part we have already discussed at the time of equation number 15. Is while writing equation number 15, you can just look at it here. Okay, so here suppose if the rho A, the atomic density operator is having only the one probability, the one EE plus 0 GG, then density operator is of this form. So remember, this is your PE and this is your PG. Okay, so if you just take the inner product of rho A within EE, we'll get the probability to find the excited state, and this would give the probability to find the atom in the ground state. And therefore its sum must be equal to 1, because the atom, in case of atom, there is only two possible states, so the sum of two probabilities must be 1. So that is rho E A of t plus rho GG A of t must be 1. And the inversion can be defined as a difference between these two. So let this be equation number 24, question number 25. So using 24, I can rewrite my inversion. So inversion can be written as 2 the atomic density operator, the reduced density operator of atom in a rho A EE of t minus 1. Okay, so let this be my equation number 26. Okay, so we have already found the expression for rho A EE of t earlier. So this is nothing but the inner product EE with sum over n equal to 0 n rho of t n. Okay, so I am going to just rearrange it slightly. So just let us take this summation outside, sum over n equal to 0 to infinity n e rho of t e n. Okay. Now we know this inner product is commuting, so we can first take the inner product of E rho of TE, and the inner product E rho of TE is nothing but C of T rho f of 0 C of T. So when we get this expression, because if you look at the matrix element of rho of T, so this is your, this element is E rho of TE, and so that result I have used, and I can write my rho a e of t. Okay, so just substitute this expression to here. So this becomes c of t rho f of 0 c of t, and this c of t, the values we already know. The c of t is nothing but cos of lambda t square root of a dagger, and square root of a dagger can be written as a dagger is nothing but a dagger a plus 1. So therefore c of t into c of t is cos square of lambda t square root of a dagger a plus 1, and we have arrow f of 0. Okay, now cos square lambda t square root of a dagger a acting on n would give cos square lambda t square root of n plus 1, and we'll have living with an inner product n rho f of 0 n. Okay, so if the field is initially in the pure state, suppose the field psi f is sum over n equal to 0, Cn get n, then rho f of 0 is outer product psi f. So this can be a sum over k equal to infinity, m equal to infinity. I have used different index instead of n, I have used k and m. So ck cm star, the outer product km. Now you can find its matrix element. So n rho f of 0 n, it is sum over km ck cm star. Then we'll get two inner product, one is nk and other one is mk, and these two inner product, this would be the canonical delta nk, this would be canonical delta mk. And if you are summing over k and m, just replace k with n, just replace k with n and replace m with n, it will become mod cn square. So the inner product n rho f of 0 n, if you are starting with the initial pure state of this particular state, then it would be mod cn square. Okay, so before going to the further, I will just write the equation number here. So let this will be my equation number 27, and this is my equation number 28, and this will be my equation number 29. So you can use this equation number 29 in equation number 27. So if you use equation number 29 in equation number 27, then the rho a e of t is sum over n equal to 0 to infinity cos square of lambda t square root of n plus 1 mod cn square, or I can write sum over n equal to 0 to infinity mod cn square cos square of lambda t square root of n plus 1. Let this be my equation number 30. And finally the inversion. The inversion is w of t, it is 2 times rho e of t minus 1, it is 2 sum over n equal to 0 to infinity mod cn square cos square of lambda t root of n plus 1 minus 1. Okay, now this can be applied in many cases. So particularly if the field state in the mixed state. Okay, so we have already reached this expression earlier, but particularly when the field is initially in the coherent state. So only what you have to do is I have to just substitute what is the expression for the corresponding the probability for to find the atom in the end state, because if the field is initially in the coherent state, the coherent state alpha can be written as n equal to some or n equal to 0 to infinity Cn ket n, and what is the Cn there? It is e raised to minus mod alpha square by 2 alpha raised to n divided by square root of n factorial, and correspondingly we can find out what is your mod Cn square. Okay, so this kind of expression we have already discussed earlier, that is if the field is in pure state, but here we are mostly interested in the field is also in the mixed state. So if the initially if the field is in the mixed state, suppose rho f of 0 is sum over n p n outer product n n, then your n row f of 0 n would be equal to Pn. Okay, let us keep some equation number here. So let this be equation number 31. This is equation number 32 and equation number 33. And use your equation number 33 in 27. So what is equation number 27? Okay, so this is your equation number 27. Rho A E of t. So if you just substitute this n rho f of 0 n of equation number 27 using equation number 33, I will get rho A E of t is sum over n equals 0 to infinity Pn cos of 2 lambda t root of n plus 1. Okay, now we have to know what is the Pn, the probability of the incoherent superposition for the to find the field in the nth state in the Fock state n. Now we have no certain distributions. So one particular distribution is the thermal state. So if the field is in thermal state, then the probability n, Pn, is given by e raised to minus En by kBt divided by sum over n e raised to minus En by kBt. Okay, so we can substitute this Pn in equation number 34. Okay, so what is En? En is n plus half h cross omega. So we can substitute equation number 35 in 34. I can get what is my rho A. So rho A E of t, it is sum over n equal to 0 to infinity e raised to minus En is n plus half h cross omega divided by kBt divided by sum over n e raised to minus n plus half h cross omega by kBt. So I have to use some other index here. Sum over m would be better into cos of 2 lambda t square root of n plus 1. So this should be my rho A, and from this rho A I can calculate W of t. It is 2 rho A E of t minus 1. And so from that we can calculate what is the inversion, and inversion of such thermal state for expectation value of the photon equal to 2 is approximately given by this graph. Okay, so what is happening here? So if you look at this expression, if you look at this graph, suppose the atom initially in the ground excited state, atom initially in the excited state, so therefore the inversion starting from 1, but the inversion never reaches minus 1. So that means if initially the field is in the thermal state, then in the time evolution the atom is always in the superposition of the ground and the excited state. Okay, it never reaches the excited state completely, or it never reaches the ground state completely. It is always in between. If you look at this expression, W of t is always in between the 1 and minus 1. Sorry, W of t is okay, so W of t is always between the 1 and minus 1. It never reaches 1 or minus 1. Okay, so that's all about how to solve the JCM dynamics if the atom and field initially in the mixed state. Okay, so I will just summarize what we have done. Okay, so if you have atom and field, the finally the density operator of the combined system I can write as rho A of t, rho f of t, and then rho of t. So initially rho of 0 I can write as rho A of 0 times rho f of 0. Now it is possible to find the matrix element of rho A E of t and rho A GG of t. Actually this is not required, so you have to just find rho E A of t, and the W of t is nothing but 2 rho A E of t minus 1, and this is what we are interested, the inversion operator. And how to get this rho A, because we know that the time evolution rho of t is u of t, ui of t, rho of 0, ui dagger of t, and we can find the reduced density operator of this density operator of t. It is nothing but sum over n equal to 0 to infinity n rho of t n. And what is the first element of this reduced density operator? That is simply e rho A of t e. Okay, so first I have to establish what is meant by initial density matrix rho of 0. So rho of 0 is simply the tensor product of ray A of 0 and rho f of 0. And suppose if initially the atom in the excited state, then rho A of 0 is nothing but EE. If in okay, so there are different possibilities. So in general, rho A of 0, it is PEEE plus PGGG. So these are the a general state for atom. And rho F of 0, it is in general, it is sum over n Pn out product Nn. Okay, so these are the initial state. So from this you can calculate what is your rho of 0. Okay, so from these two, just substitute this here and just substitute it here. I can find out rho of 0. I can find out the matrix form of rho of 0, and from the matrix form of rho of 0 I can calculate my rho of t. And once you calculate rho of t, I can calculate the reduced density matrix rho A, then its first element rho A E of t, and from this we can calculate what is your W of t. So that is the complete thing. And for the case we have discussed now, so in here I have assumed the atom is initially in the excited state. The atom, we have assumed the atom is initially in the excited state, and the field is in the incoherent superposition. That is sum over n equal to 0 to infinity Pn outer product Nn. In this particular case, the form of W of t is already given here. It is would be 2 times sum over n equal to 0 to infinity Pn cos square lambda t square root of n plus 1 minus 1. So this is for this particular example that we have discussed here, but in general it need not be of this particular form. The form may be different. So for that it will be completely depending upon what is your the initial state of the atom and your initial state of the field. Okay, so here we have assumed the atom initially in the excited state, so that is why the inversion is starting from plus 1. If you assume the initially the atom in the ground state, then it would have been started from minus 1 W of t, might have started from minus 1. But anyhow, you can check it out whether the atom started from the ground state or start from the excited state. Then in the time evolution, if the system is in the thermal state, if the initial field is in the thermal state, then the time evolution is slightly complicated. Okay, and if the time evolution for the initial state as a coherent state, if the initial state is coherent state, then the expression we already known earlier, we have seen that there is a possibility of collapse and revival, etc. So that kind of things happen if you look at the equation number 31. And you can consider the field is of some other state as well, some other pure state as well. So everything you can solve it from this particular approach. So whether the system is initially in the pure state or in the mixed state, you can use the density operator approach to solve it. Suppose the atom, I already said, suppose the atom is in the atom, initially atom is in the excited state, then rho A is simply EE. Okay. So what is meant by, what is the corresponding state and what is the corresponding pure state of the atom? The pure state of the atom, psi atom, can be written as E. And what is the density operator for it? The density operator is outer product psi atom. So that is nothing but outer product EE. Now suppose they add the field. Okay, suppose the state of the field, it is 0. Suppose the state of the field, the field is vacuum, there is nothing. Okay, it is a pure state. Now what is the corresponding density operator? So rho f of 0, it is outer product psi f, and that would be outer product 0 0. So that is your rho f of 0. So from this we can calculate what is in by, what is your rho of 0? It is rho a of 0 times rho f of 0. So for this we have to just find out what is the matrix elements of rho a of 0. I think rho a of 0 I can simply write as 1 0 0 0, and rho f of 0, it would be 0 0 0 1. So this would be your matrix elements. Just take the inner product, you will get rho of 0, and you can find its time evolution using this expression. The time evolution you are using this rho of t, then reduce density operator and find its first matrix element, that will give the rho a e of t, that will give the probability to find the atom in the excited state. Then 2pe minus 1 will give the inversion. Okay, so in that way we can solve any of this problem, whether the atom in the pure atom or field in the pure state, or whether the atom or field in the mixed state, or in the combination. Okay, one is in the pure state and one is in the mixed state. So anyhow, all kind of the initial state, whatever be the initial state of the atom and field, all kinds of initial state is covered using this particular approach. So that is the beauty of this density matrix approach. You can solve it for any kind of problems. Okay, so that's all about the density operator approach of Jaynes Cummings model. Okay, so next we have to discuss how to realize this model physically in lab. So that we'll discuss in the next lecture. So see you soon. Thank you.